boys and girls, the whole idea here is that you are microgravity researchers and you're going to be designing real microgravity experiments. So the question to you is, what is microgravity? Small gravity. Okay, well, that sounds right. It's a good translation. Does it help if I tell you that microgravity is the technical term for weightlessness? Have you, boys and girls, have you all seen videos of what weightlessness looks like? What have you seen? You've seen astronauts floating around in space. Chris Hadfield likes to do videos, educational videos, floating around in space and singing songs in space, right? Everybody, everybody knows what weightlessness looks like. So now, boys and girls, I have to ask you, what causes weightlessness? Why are the astronauts weightless? There's no gravity in space. Wow, that sounds right. But wait a second. What causes the moon to go around the Earth? What causes the Earth to go around the sun? If there wasn't gravity in space, the Earth would just go off on a straight line into deep space. What does that mean? Gravity in space, good. No gravity in space, really bad. There is plenty of gravity in space, so it can't be that there's no gravity in space, which as the reason why the astronauts are. Now, stepping out of the moment, talking to teachers again, either tomorrow or Monday, I'm going to put up a blog post on the SSCP National blog, and it'll go to all the leadership, so Matt can pass it on to you. And it's a challenge. It's a part blog post. And the name of it is, you want me to take a bathroom scale where? And the idea of the first blog post, it will be a challenge to the students. We're looking for answers coming from the students so that they can noodle. And then a few days later, we'll post the answer. And so what I'm about to walk you through is actually on the microgravity experiment design page on the website. And it is also going to be the subject of those two blog posts. So what I'm about to say is well documented. And so I'm going to, your fifth through seventh graders again. And so boys and girls, there must be a lot of gravity in space. The moon goes around the Earth goes around the sun. That can't be why the astronauts are weightless. And you know what? I want to go up there myself and see that weightlessness for myself. But right now, at least not yet, there aren't any tickets that I can buy to take a trip to low Earth orbit. It's coming, but not yet. So I figure I'm going to go and look around far and wide for a really tall mountain that is 47 times higher than Mount Everest, so that the top of it is at 260 miles altitude. And when I'm at the top of this mountain, the International Space Station flies right by my face at 4.5 miles a second. It's really booking. And so what I'm going to do is I'm going to walk to the top. I find this mountain, and I'm going to walk to the top of this mountain. And I'm at the very top, at the same altitude, at the same place where the International Space Station is. And I'm going to look in the window really fast as it flies by my face to see if the astronauts are truly weightless. And what I've done is, what I took up to the top of the mountain with me was my trusty bathroom scale. Okay? So I'm at the top of the mountain, and here comes the International Space Station. There it goes. I look in the window really fast, and sure enough, the astronauts are weightless. It's as if there's no gravity in there at all. And now I put my bathroom scale down on the top of the mountain at the same location as the International Space Station, and I step on my bathroom scale, and here's the challenge to you, boys and girls. What do I weigh? My normal body weight? Any other suggestions? Nothing. So, and anything in between, right? Well, it turns out that if I step on my scale, I will weigh 92% of what I weigh on the surface of the Earth. So gravity has been diminished just a little bit, 8%. And what we need to understand is what weight is. Weight is the force of gravity that the entire planet Earth can muster on you. Your weight is the force of gravity that every piece of planet Earth is exerting on you, summed up. Okay? Does everybody understand that? And your weight depends critically on how far you are away from the Earth. If you're farther away from the Earth, gravity diminishes. So here we are 260 miles up, a little farther away from the center of the Earth than the surface of the Earth, and gravity has only diminished by 8%. So that little added separation between you and planet Earth has caused the gravity, the force of gravity on you to diminish by 8%. Does everybody understand that? So does that mean that gravity is alive and well at the orbit of the International Space Station? In fact, the weight of the International Space Station is what? 92% of what it would weigh if you put it on a huge bathroom scale on the surface of the Earth. So what that really means is it can't be a lack of gravity that's causing the astronauts to be weightless. And the first blog post ends with the students trying to guess what they would weigh on that bathroom scale at the top of the mountain. So now the next blog post, the answer goes into these details. So boys and girls, what we're going to have to do next is we're going to have to go to the top of a very tall building, okay? So the CN Tower is in Toronto, is that correct? Does anybody know how many floors there are? Or, well, it doesn't have floors, it's a tower, right? Let's use the Empire. Since I'm a New Yorker, I'm going to use the Empire State Building because I know it's 104 floors, okay? So I'm going to take everybody to the top of the Empire State Building to the 104th floor, and I have found an elevator whose shaft goes from the 104th floor all the way down to the first floor. So it runs the whole vertical height of the building that can be occupied. And the elevator, inside the elevator is me, my trusty bathroom scale, and a little step stool, a little chair, such that when I stand on it, I am 1 foot above, a third of a meter above the elevator floor. So everybody got that? And there are no windows in the elevator. And the elevator right now is on the 104th floor. It's not moving. The elevator doors are open. It's just sitting there at the 104th floor. And boys and girls, I get on my little chair, my step stool, and I've placed the bathroom scale on the floor a foot below me. And with the elevator not moving, I step down from my little chair, my step stool, onto the bathroom scale, and what do I weigh? Yeah, even 104 floors high building is still on the surface of the Earth. That's virtually no change in distance above the Earth. So what I would see is my normal weight that I would see on the surface of the Earth. Is everybody with me on that? Now, you might argue, well, there's got to be some difference because you're a little higher up. Yeah, but you would need a very high precision scientific instrument to measure the difference. So for all intent and purpose, you're weighing the same on the 104th floor with the elevator stationary as you would on the surface of the Earth. So now, boys and girls, I'm going to do the same little thought experiment. It's called a thought experiment. But now what's going to happen is I'm back on my chair, back on my step stool, and the moment I am walking off the step stool, heading towards the floor, the doors close and somebody cuts the cable on the elevator. So what happens to the elevator? So the weight of the elevator, the entire force of gravity that the Earth can muster on the elevator, is now acting on that elevator, and there's nothing to hold it up against that weight because the cable was cut. So the elevator is said to what? It's said to accelerate, right? It's the force acting on it is causing it to go faster and faster and faster. Do any of you students know what the acceleration is due to gravity? Oh, An English unit from a Canadian community? Okay, yes, it's 32 feet per second, or 9.8 meters per second, which means that every second it is moving 32 feet per second faster, which is the same as 9.8 meters per second faster. Everybody understand that? And is it true that gravity is working its will on not just the elevator, but everything inside the elevator, that everything is being pulled down with an acceleration of 9.8 meters per second per second? Yes. So this elevator is plummeting at an accelerating rate towards the ground floor. But inside the elevator, do I see anything move? Why? Because there are no windows, right? And is it true that the moment the cable was cut, I was already starting to head down towards the floor because I was just stepping off the chair, just stepping off the step stool. So is it true that I am now accelerating in the direction of the floor at 9.8 meters per second per second? But is the floor and the bathroom scale accelerating away from me at exactly the same rate? So am I approaching the floor? No. What do I see? I'm weightless. I'm floating in the elevator. There's no up, there's no down. I could push off the sidewall, travel over there, travel back. I can do whatever I want. Does everybody understand what I just said? If everything is accelerating down because I cut the cable, then I am accelerating in the direction of the floor at 9.8 meters per second, but the floor and the bathroom scale are also accelerating away from me at exactly the same rate, 9.8 meters per second. We're all doing the same thing. So I never get to the floor until I get to the first floor, and hopefully someone will put the emergency brakes on. Does everybody understand that? Okay, so now I have here, I'm sorry, this is the first page of your implementation plan. Matt, I do not mean anything by this. I forgot to bring my ball, so I have a little ball here. So boys and girls, I'm going to throw this ball, okay, that way, horizontally. Can somebody describe the path it took? And for those of you who know something about physics, the shape of that curve is a parabola. It's a parabolic trajectory. But anybody who does anything in sports, anybody who's had just a casual catch with mom and dad or their friends, they know how gravity acts on something that you throw. It causes an arc. And what's really interesting is what I'm about to say, boys and girls, because most human beings alive on planet Earth don't recognize what I'm about to say. Imagine that ball that I threw and it followed an arc and the Earth's surface stopped it, so it just stopped over there. Imagine the Earth would allow the ball to go through the Earth, continue moving on, and gravity is still operating in full on that ball. If I throw the ball, it will not stop at the surface of the Earth. It'll magically keep going. Most of the mass of the Earth is beneath the ball, so it's accelerating the ball at a faster and faster rate. And then eventually the ball is going to go past the center of the Earth, 4,000 miles below us, and realize that most of the mass of the Earth is above it. And so the Earth says, come back where you started. And so the ball starts to slow down after it passes the center of the Earth because most of the Earth is above it, pulling back up, and it completes an arc. And it comes around and it pops up outside the surface of the Earth on the opposite side from where it went in, and I can catch it in my hand. So this is Bullard, Texas implementation plan. Boys and girls, this is a piece of an orbit. It's a piece of an orbit. You never see it go through the Earth. The Earth stops it. But if the Earth did not stop it, it would continue to go right thousands of miles down, right past the center of the Earth. It would go to the opposite side of the planet. It'll then whip its way back, come back here, and I could catch it in my hand. That is a piece of an orbit. Now, if I throw a ball horizontally faster, what happens to the arc that it travels? It's a larger arc, right? And if I keep throwing the ball horizontally faster, it makes a larger arc and a larger arc. And eventually, if I throw it fast enough, it'll make such a large arc that it completely circles the Earth, never intersecting the Earth's surface. Does everybody see what I just said? And there's a graphic on the experiment design page. There is actually a link to a graphic showing the famous cannonball graphic where you have a cannon on top of a mountain. And it shoots at an ever increasing horizontal speed, and you see it hitting the Earth, and then finally going completely around the Earth. Well, this is the implementation plan for North Star Public Charter School in Idaho. So boys and girls, this is the International Space Station. That's the moon orbiting the Earth. That's the Earth orbiting the moon. That's the whole solar system orbiting the center of the Milky Way galaxy every 250 million Earth years, which is defined as a galactic year. And 1 galactic year ago, the dinosaurs roamed the Earth. Isn't this like so cool? All of those phenomena are exactly the same thing, okay? And here's a misconception. We typically think that when something is falling, it's getting closer to the Earth. And the only reason we think that is because that is our experience. But something that is falling, and another way to say it, which is what one of you said earlier, is free fall. It's called free falling. And what that means is that the only force acting on an object is gravity. If the only force acting on an object is gravity, it is said to be in free fall. And what's really ironic about this story is go back and think about the elevator. What was causing the elevator to accelerate at that high rate? What was causing the elevator to accelerate when we cut the cable? Gravity, right? So there's this enormous gravity that is being provided by all of Earth, working its will on the elevator, pulling it down at an ever-increasing speed. And the irony is, inside that freely falling laboratory, it looks as if gravity is turned completely off. It's gravity that's causing the effect, but inside the laboratory, it's as if gravity has been turned completely off. And any system that you put in that elevator is going to behave as if there's no gravity. And we've just demonstrated that that elevator is the same thing as the International Space Station.